So some housekeeping before we start. We will be recording this session, but we will turn off the recording for the hands-on part so you can ask us lots of questions. So if you'd prefer not to be on camera and being recorded, then now's the time to turn your camera off. If you have questions during the presentation or demo, then you can type these into the chat box at any time and we'll try and answer as many as we can as possible. So we all get familiar with the chat box. Can we navigate to it now and tell us where you're joining from? So hopefully you should see the little chat box along the top. And I can see people starting to tell us. So we've got Austria and Belgium, Munich. That's great. Poland. So while you're doing that, let's just have a look at what we need for the hands-on part. So for the hands-on part, we'll need CSD CrossMiner installed with an active CSD Discovery or Enterprise license. And you'll also need the workshop handout. So you should have already received an email about where to find that, and we'll also post a link in the chat box. If you don't have CSD CrossMiner installed yet, then unfortunately you won't have time to install all of our lovely software and data before the hands-on part, but you can still follow along to our presentation and demo and then try our hands-on part later. If you have installed CSD CrossMiner but you haven't opened it yet, then just to let you know, it does take a while to load the first time of opening, so you probably want to do that before we get to the hands-on part. I can see some more countries coming in. So Cambridge, UK, Brazil, Malaysia, Spain. That's great. So over the next 90 minutes, we'll be showing you how to perform Pharmacophore searches using CSD CrossMiner before you get to try some examples in our hands-on exercises with your tutors on hand to help. We'll finish by exploring a case study and then we'll see what we've learned together in a fun quiz. By the end of the session, we should all be familiar with what the CSD CrossMiner software looks like. We should know how to interact with a pharmacophore, how to perform pharmacophore searches, and how to analyze results. So let's meet today's hosts. So I am Susanna, and I'm joined today by your tutors. So with me today, we've got Ilaria, Francesca, Elenia, Abik, and Eva. So we've introduced ourselves. So as usual, let's find out a bit more about you. So you should hopefully start to see a poll on your screen so you can tell us if you've attended a virtual workshop before, if you've visualized or explored protein ligand structures before, if you've visualized structures using Hermes or Mercury, if you've used CSD CrossMiner, if you've used another CSD discovery program, or none of the above.
So I'm having some issues with the poll. So if you want to let us know in the chat for the time being. It's probably live now, but it's, yes, sorry.
Okay, so we've now got the poll. So have you done any of the following before? Attended a virtual workshop, visualized crystal structures, used CSD CrossMiner or another CSD discovery program? So you should see the poll pop up that you can answer and start to submit your answers. And I'm starting to see the responses. So it looks like quite a few of you have explored protein ligand crystal structures before. Some of you have already used Mercury's, Hermes, CrossMiner, and Discovery programs. So while you're filling that in, let's have a look at some crystallographic databases and remind ourselves what databases are available. So at the CCDC, we curate the Cambridge Structural Database, which covers organic and metal organic structures. But alongside the CSD, the Worldwide Protein Data Bank manages the PDB of macromolecular structures, and you can do pharmacophore searches across both the CSD and the PDB using CrossMiner. As well as the CSD and the PDB, FITS Karlsruhe in Germany curate the Inorganic Crystal Structure Database, and we have joint access and deposition services to enable you to access and deposit all small molecule structures more easily. And finally, there is also the ICD database for powder diffraction files, and their PDF for organics database includes data derived from the CSD. So let's have a quick reminder of what is in the CSD. So the CSD, as you've hopefully seen before, was established back in 1965. It contains over 1.1 million structures and every published organic or metal organic structure. And it includes structures associated with scientific articles, patents, repositories, thesis publications, or those published directly through the CSD as a CSD communication. It is really a community effort with structures determined by crystallographers globally, and every single CSD entry is enriched and annotated by experts at the CCDC. So that's to aid the discoverability of data and the knowledge from the resource. And you can see the growth of the database here since 1972. And you can see one of the structures that we call kitten. So, and hopefully you remember what kitten is if you've attended one of our virtual workshops before. So as well as being a cute cat, kitten is a CSD ref code. So a CSD ref code is a database reference containing 6 to 8 characters. It's used to identify entries in the CSD. The same substance is in the CSD are assigned the same 6-letter code with an additional 2 numbers if they're in the same ref code family and they're the same substance. So when we're looking at CSD CrossMiner, we might see some of these CSD ref codes popping up. Some of my favorite ref codes are listed here, and some are more familiar kind of sounding names. So we've got, alongside kitten, we've got Disney. We've also got one ref code named after somebody. So we've got Gautam, but you might be able to find a ref code that's similar to your name. And we've also got chemical sounding ref codes like glycine. So if you do have a favorite ref code, or you can find a ref code similar to your name, then do post it in the chat box. So as I'm sure you know, the CSD contains a mix of organic and metal organic structures with single and multi-component complexes, and it's used in a variety of industries, and particularly relevant for today is the pharmaceutical industry. It contains a wealth of information about lots of different structures, and these include drug structures. And you can easily access approved drugs using our drug subset that you can find in Conquest and our Python API. But we've also got other subsets like the COVID-19 subset. So if we have a look at some of the drugs in the CSD, we can do this by looking at the top 200 drugs by retail sales, which was a poster published and compiled at the University of Arizona in 2018. And on this poster, you can see that the top 200 drug structures, which are also in the CSD, are listed in green. So you can see there's really a wealth of information about the drug structures in the CSD. If you want to learn more about the drugs in the CSD, then we've recently published a blog about the FDA's drug approvals in 2020, so do check out our blog space. As well as drug molecules in the CSD, it also contains ligand structures such as glycine. And here we can see a protein structure in the PDB, and you can just about see a ligand. So we can highlight that ligand in blue. So this is what it looks like in the PDB. And then you can also see what that ligand looks like in the Cambridge Structural Database. There are links between the ligands in the CSD and the PDB ligand chemical component dictionary to enable you to navigate between the two. But as well as linking between the databases, you can explore the databases together, and that's just what we're going to be doing today using CSD CrossMiner. So now we've been reintroduced to some of the crystallographic databases and the CSD, let's hopefully do a few more questions about you. So which databases would you like to search using CSD CrossMiner today, and what sector are you in? So you should hopefully see the poll being published now. I can see some answers coming in. So I think at the moment 66% of you like to search the CSD, about 30% the PDB. So we'll give people a couple more seconds to answer that before we do the sector poll. Okay, we'll put the next poll up. Thanks. So while you're filling that in, let's have a look at the CSD portfolio. So to help us get the most out of data in the CSD, we have a range of associated software to help us search, visualize, and analyze and learn from the data. Today, we're going to be using CSD CrossMiner. So you can find CSD CrossMiner in our CSD Discovery Suite. And CSD CrossMiner allows you to do Pharmacophore searching across the CSD. So with that, I am going to pass on to Francesca, who's going to take us through CSD CrossMiner.
Okay, CSD CrossMiner. So thanks for joining to this webinar and to this workshop. And today we'll be focused specifically on CSD CrossMiner. So first of all, what is CSD CrossMiner? So as written here, it is a tool. It's an interactive tool for Pharmacophore-based searches of structured databases. If you are not familiar with the term Pharmacophore, I have included a couple of definitions here. So one from UPAC and one from Wikipedia. So from UPAC, you can see that a Pharmacophore is defined as an ensemble of static electronic features that is necessary to ensure the optimal supramolecular interaction, while Wikipedia kept the definition a little bit more general, defining as an abstract description of molecular features. And we will see that this second definition is more aligned with the underlying concept of the CSD CrossMiner. So what you can do with the CSD CrossMiner? So CSD CrossMiner allow you to simultaneously search structured databases. With the application, we provide the PDB and the CSD. So this will allow you to retrieve valuable information that can be used in a drug design project. But we also allow the possibility to add your in-house databases, and you can generate the databases using a GUI or with the CSD Python API. So because the Pharmacophore-based search tools can be time-consuming, CSD CrossMiner was specifically designed to enable on-the-fly hypothesis testing with the near instantaneous results. This makes the search in CSD CrossMiner much faster than with any other tool. So the entries in the databases are annotated with information related to the crystallographic structure. For example, for CSD, you will see the ref code that Suze have described before. While for PDB structure, you can have information about the EC numbers or the PDB molecular resolution and many more. So this annotation can be used not only to retrieve information about the structure, but also to filter your results. For example, to retrieve only specific types of structure that match your Pharmacophore query. What can you do with the CSD CrossMiner? So CSD CrossMiner allows you to understand protein-ligand interaction. So for example, starting from a structure of protein-ligand complex like displayed here on the left-hand side, you can translate it in a Pharmacophore query like showing here, and so describe the binding site and the protein-ligand interaction in a much easier way. So from here, you can determine common protein binding sites in the PDB structure, or you can also determine structural motifs that bind in similar environment. And this can be really useful to shed some light in the cross-pharmacology between the protein targets, and as well into the selectivity of bioactive small molecule with the further implication to toxicity and adverse reaction. Accessing crystallographic databases by using such generic features can give impetus to on a research project by generating new ideas. So, for example, you can design a novel motif that mimic established ligand. This can help to move away from an already patented chemical space or to improve physiochemical and pharmacokinetic properties. This can be also useful to retrieve a diversity of ligand topologies that can be used as scaffold, and also to look at chemistry that may interact with an explored part of the binding sites. So this can really help with improving the selectivity of the ligand, for example, against a protein of the same family. And therefore, again, we can be really useful to reduce cross-reactivity and improving bioactivity as well. So how does it work? So each entry in the database that is provided with the application is annotated with features. A feature can be defined as an ensemble of steric and electronic features that characterize both the protein and small molecule. The features are defined using smart patterns and are stored in a feature database that is, again, provided with the software. So the features definition are user editable. So this means that they can be tailored by the user. And in addition, new features definition can be easily created and applied on the fly. So I think I'm not, okay, features represented as sphere as displayed here. So, and they have also different colors. So you will see that acceptor, for example, is colored in red, donor is colored in blue. A feature can be single point, like the halogen highlighted here, and are located on the atoms. Features can also be directional, as acceptor features here in red, and are represented with the 2 or 3 small spheres, where the base of the features is located on the atoms, and the directionality is represented by these translucent spheres. So the actual Pharmacophore query doesn't work with the features, but actually works on generating a feature, the Pharmacophore point on top of these features. So they can be easily generated starting from the atoms and are defined using the same types of feature, but in this case with the tolerant spheres. So where the radius of the sphere reflects the uncertainty in the position. So this means that the larger is the sphere, the larger is the uncertainty allowed for the match. As for the features, Pharmacophore point can be either single point or directional, therefore represented as 2 or 3 points, like acceptor projected here and donor projected. So as a Pharmacophore, the Pharmacophore query can be further customized by defining the nature of the Pharmacophore point, where a Pharmacophore point can be set to belong to a small molecule, to a protein, or to any of the two. A Pharmacophore point query can be further customized by defining the constraints. So it is possible to define an intramolecular constraint, which requires the Pharmacophore point in the matching structure to be located in the same molecule. So such constraint is represented by a green dashed line between Pharmacophore points. You can also define intermolecular constraints, which require Pharmacophore points in the matching structure to be located in a different molecule. So intermolecular constraints are represented by a red dashed line between the Pharmacophore point. You can also define no constraint. So in that case, hits of both kinds can be found, and there are no dashed lines between the Pharmacophore points. So when you define your query, you can then easily start the search in CrossMiner by playing using the play button. So, and you will see immediately results populating the 3D view, but also the resulted list. So the hits will be overlaid to your query, and you will retrieve several information of the hits matching the pharmacophore point. So I will go more in details about these in the during the demo. So, and I think I'm going to give it now to Ilaria, that is going to describe a little bit more the CrossMiner interface.
Before diving into the demo, we just wanted to show you more of the CrossMiner interface. So this is how CrossMiner looks like. And if you click for me, Francesca, on the right-hand side, you can see the three boxes appearing. The top one shows the feature databases. The one in the middle shows the results hit list, so all your results, as you saw in the video, will appear there. And at the top, you see the annotations for each column. And at the bottom, you can see the Pharmacophore feature with the color code, and you click on each to expand and learn more. In the next slide, we see some of the basics to move your structures and features pharmacophores in the 3D window. So if you click with the left mouse button and move, you will rotate your structures and pharmacophores. If you use the middle mouse wheel, you can move your structures and pharmacophores up and down. The right mouse button, click and hold and move up and down, works as a zoom. Shift and left mouse works to rotate your features in the plane, and control left click is to move structures in the plane. If we use the right click on a pharmacophore point, you will see this menu appearing, which is the Pharmacophore context menu, and you will be using some of these options during the hands-on part. If inside you right click away from a feature, the 3D view menu will appear, showing you some of the 3D view options indeed. Next, we'll see some of the menus. We'll go fast through this. Most of the things we will be seeing today are from the File menu. Then there is the Edit menu, Display, and the toolbar options to retrieve if you close any of the toolbars. And then there is the Feature Database and Help menus. Another couple of things to know about the interface. So on this bar, you can select your picking mode, which it can be normal, so picking each of the features. You can use lasso to select a group of features, or you can measure distances, angles, and torsions. Then we have the edit button. So when you have the hands open, it is the edit features are off. If you have the hand closed, it's on. I happen to make a number of mistakes forgetting that the edit was on, so Control Z was a very good friend in those cases. Then we have next to the edit button, we have the search button. So we have play, pause, and stop the search. And then we have some of the styles and colors options, which were shown in the short animation. So we saw wireframe, capstick, and ball and stick options.
So I think it's next to me now. Thanks, Ilaria, for the nice overview of the GUI. So for the demo today, I'm going to use a Pharmacophore query generated to describe the S3 pocket of the human cathepsin L protein in a complex with the nitrile inhibitor, like displayed here. So we will then use this query to look for ligand fragments that are known to bind the similar protein environment, and we will also take a look of protein that share similarity with this pocket. But we are also going to change the nature of few pharmacophore points and see how this search is evolving. But the purpose of this demo is to just show you full functionality. So first thing that you have to do actually to run a Pharmacophore search is to generate a Pharmacophore. So you have several options in CrossMiner. So you can start from your molecule, so for a reference, and you can easily load it by clicking on load reference. Or you can also browser to the database and pick one of the structures that is in the database. So for example, in this case, I'm going to browser to it. You will have you can see all the structure that are into the databases, included the PDB and the CSD. So for the purpose, so the crystal structure, the PDB ref code for these catepsin complex is 2XU1, and I can use this structure, and I will click use as a reference to load it in the 3D view. So by default, all the acceptor and donor features associated with the structure will be displayed in the 3D view, and you can use this feature to actually generate the Pharmacophore point. So I'm going to add hydrogen, so this makes things a little bit easier. You don't have to stay with these features, but you can display all of them by clicking on all in showing reference, or hide it all by re-clicking, or just selecting the one that you are interested in. So for time-wise, I'm not going to generate a Pharmacophore query here, but what I'm doing is to load a pre-generated Pharmacophore query. So to do so, I'm going to use the load Pharmacophore option in the menu, and this will open the example Pharmacophore folder that is provided with the application. And I'm going to load this structure here, that is CATL_S3, that is actually the query of the pocket S3 of the catepsin. If I open, you will now see that the Pharmacophore query is displayed in the 3D view, and is also overlaid with the residues that are coming from the database. This is because I generated the query from this structure. So I'm going to let's take a look a little bit of this query. So I'm going to label the carbons, the residues by alpha carbons, and I'm doing from the 3D right-click menu. So clicking on label and display protein residues. So now it's a little bit more clear about what these Pharmacophore points or which residues they belong. So if we take a look now, so we see that this query is composed by two acceptor projected that are belonging to a protein. So it's P that is defined as a protein, and they are on the oxygen of the carbonyl of the glycine 61 and on the oxygen of the glycine 68. So we also have a protein donor projected on the glycine 68, but is located on the nitrogen. And we can see that this pocket is also characterized by an hydrophobic part, and therefore the hydrophobic region, the hydrophobic Pharmacophore point has been built on the side chain of the leucine 69. So you can also see that you can notice that some Pharmacophore points have smaller radii than the others. This is to ensure that hits matching these Pharmacophore points are with very close alignment to the center of the Pharmacophore sphere. In addition, to be sure to retrieve information about ligands that are interacting with these pockets, we have generated also two Pharmacophore points for the ligand that is displayed as S here, that stands for small molecule. So these Pharmacophore point has been kept generic, so like heavy atoms. So this means that hits will match any atoms that is not hydrogens. We also use the intramolecular constraint between these two Pharmacophore points as displayed by this dashed line. So this means that hits matching these two heavy atoms will belong to the same structure. So the Pharmacophore, the information about the Pharmacophore points, so the nature and the sites, are also displayed in the Pharmacophore features window here. So you can enlarge or smaller the size as you wish. And you have information about the values, so what is the radius of these pharmacophore point. And for the projected one, you have information about the size of the base and the size of the projection. You see here that all the pharmacophore are visualized, but you can decide to hide some of them by enable or disabling these showing pharmacophore. So I'm not going to use the reference for anything else, so I can clean my 3D view by closing the reference, and I will do it going from the File menu. So this will only leave the pharmacophore query in the 3D view. So after this, I'm going to start the search by clicking the play button here. So you will see that the results that are matching these pharmacophore query will be immediately loaded in the 3D view and listed in the result it list. So the hits are overlaying the pharmacophore query. So this is providing a really nice visualization of the part of the molecule that are matching the pharmacophore query. So we can take a look at the single structure by clicking on them. You can use your mouse, or you can also use the arrows on your keyboard to scroll to the results. But in case you want to visualize again all of the results, you can easily show all of them by clicking indeed on Show All. So now we are going to take a look a little bit of the results it list windows. And so therefore I'm going to pause the search. This will make things a little bit clearer, and I can spend some time here. So by pausing the search, you can see that the number of hits that we have found so far is 520. But of course, this number will change if the search is still running. So in the result it list, you have information about the identity. For example, to have it again, you can enlarge this window to visualize all the name. And you have the information about the PDB code that is matching, that is from where this binding site has been generated. And the color of the identifier actually represents the database where it's coming from. So in this case, is orange, so it means that it's coming from the PDB. So by default, the results, so the hits they are matching the pharmacophore query are clusterized based on the Tanimoto threshold that is shown here. So therefore, only the cluster representative is displayed. So you will only see one structure for cluster 1, 2, and so on. You can visualize, you can easily access to all the cluster representative by unticking this first in cluster button. And you can also sort by cluster number by clicking on the cluster header here. So now you will see that you have more structure that has this cluster 1 displayed. So we can then reclusterize again, and in this case, this will be only reflecting on the resulted list. So it's there. So the RMSD value, so of the overlay, is also provided. So this is giving information about how well the hit matching the pharmacophore query is overlaid to the pharmacophore point. So this means that lower is this value, better is the overlay. You can, as for the cluster, you can sort by RMSD by clicking on the header. So by, for example, having the lower RMSD on the top and the higher on the bottom. So the 2D diagram of the hits is also displayed. So this will provide information about the atoms of the hit that are matching the pharmacophore query. So this header, this window again is resizable, so you can enlarge it or you can decrease it the size as you please, and you can also hide it if you want to have more list displayed in this window, for example. So you will see here that there are several other information. So those are the annotation that I was talking about during the presentation. So each hit is coming with the different information, so the position, date, easy numbers that can be used to actually understand what is your hit and what is matching. So what is the hit matching the pharmacophore. So in this case, for example, if we go to the molecule, we can see that the hit with the lower RMSD is matching the flavodoxin that actually is a structure, is a molecule different from our original structure. So where this query was generated, that was catepsin. So this search is on the hypothesis really early and is already provided 500, more than 500 results. So this can be is likely due to the large radius of some of the features. So therefore, maybe lowering the radius will provide less results with more precise alignment to the pharmacophore center. So we can test these hypotheses, and I can, for example, stop the search and edit the radius of this feature by using the Pharmacophore feature window. So I'm going to change only a few of those, and in particular, I will focus on the acceptor projected. So I can change the radius by double-clicking on the tolerance radius and decrease it to, for example, 0.5. And I'm going to do the same also with the virtual point. And this is the base of the projected 2 is already at 0.5. So I'm going only to change the virtual point. So this you can see that is easily reflected in the 3D view. So I'm going to play and start the search again. We can easily start to see results almost immediately. And we can actually see that we can again enable the diagram to see what kind of hits are matching the pharmacophore query. We can again enlarge, and we can take a look at the annotation on the fly. So we can actually start to see now that the hits with the lower MSD are indeed catepsin. So in CrossMiner, I highlighted before that you don't have to, you can verify your hypothesis on the fly. So for example, you can change the nature of the pharmacophore point while the search is still running. So for example, we can access the right-click menu on the pharmacophore point to select one. So I'm selecting hydrophobe here and changing into something else. So you have a list of all the features that you can use. But in this case, I'm going to change completely the nature of the pharmacophore, going from an hydrophobe point to a water, so hydrophilic. So you start to notice that there are a few things that has been changed. So the results of the 3D view has been cleaned, and also the resulted list view, because I changed my hypothesis. So the software is responding by restarting the search. So also the hydrophobe features that was listed here is not listed anymore, but we will find the water features on the bottom here. We can also change the radius, so I'm going to decrease and see this is again starting the search. So in this case, for example, if you want to change the radius of one single pharmacophore point, you can again using this window, or you can access to the right-click menu. So from here, you can decide to constrain the molecule with something of the same nature, for example, to heavy atoms here. You can morph it in something else. I use it for water, but you can select as many features as you want. And you can also change the radius of the pharmacophore point to increase or decrease based on your need. So we can start to see some results. So you see that this search is a little bit slower, or is providing, let's say, less results. So consider that we have defining a binding site that is described the S3 pocket of catepsin, and we completely changed the nature of the pharmacophore point from hydrophobe to water. So we can hypothesize that there are less results because this pocket is hydrophobic, it's really hydrophobic and doesn't accommodate any water in this part. So again, if we want to validate this hypothesis, what we can do is to move the pharmacophore point, so like moving a little bit further from the pocket. And again, you don't have to stop or pause your search to do so, but you can use the Pharmacophore edit menu to do so. And you will see that the hands here is changing from open to close, that means grabbing, and also your mouse is changing. So I'm going to move the water here, so far away from the binding sites. And again, this will restart the search, and the new results will populate the 3D view and also the resulted list. So I'm going to close the edit so I can easily see what is happening. And also if I zoom into this water pharmacophore point, you start to see water molecules that are populating this area of the pharmacophore. So we can, from here, we have also several options. So we have changed our pharmacophore query. So maybe we want to resave it. We want to save it. To do so, we can click on File and Save Pharmacophore. So this allows you to save the pharmacophore in a folder of your where you prefer to save it. So for example, I can change it with water. So this is going to save this pharmacophore query, and you can reuse it next time and load it and perform a new search or changing again the hypothesis. If you want to save the results, you can do it in 2 times, to be honest, so to say. So you can wait for the search to finish, and you can, or you can, if you are happy with the results that you have received so far, you can pause your search, and from File, you have all the option to save the hits. So you will see that there are 3 options. So you can save marked hits. So that will be saving everything that is these checkbox here marked. Or you can also have the option to save what are visible hits. So everything that is displayed in the 3D view. Or you can save all the hits, so means all these 170 structures that has been found so far. But of course, if you wait the end of the search, this number will probably change, will be probably increasing, and you will save all the results. You can also save the pharmacophore query or the structure or everything that you have in 3D view as an image. So you can use it for a poster, for PowerPoint, or for document. Or you can also save export in PovRay. And I want to highlight that you can also save the pharmacophore in a format that is compatible with the third-party tool.